how the gastric phase kind of works. As a review, when we detect that there are amino acids, polypeptides in the environment, we activate our G cells. They put out a molecule called gastrin. Gastrin will activate parietal cells that put out hydrogen. Hydrogen is in the lumen. It activates other sensory neurons that tell the cell to put out pepsinogen via the chief cells. This hydrogen ion will then tell D cells to put out the inhibitory molecule somatostatin, which will then inhibit the G cells, parietal cells, and the chief cells. Kind of a complicated process. Go over it a couple times. Hopefully it makes sense after a while. But this is basically the idea of put out acid and enzymes, but when you put out enough, stop. This is just a way of putting a decent amount of it out into the lumen and then stopping after a while. Because if you get the sense of amino acids, and if amino acids are in your stomach, you're just going to keep on putting acid and enzymes in your stomach non-stop. But then with the somatostatin, you can then stop it after a while. And so the main players here are gastrin, hydrogen ion, and somatostatin, and pepsinogen. So if you can remember how these four things work, it'll be a little easier to balance this all out. All right. Can I move on? Yeah.
How do the D cells arise?
D cells will detect. They just detect acid.
So you have a high acid, and the D cells.
The D cells will activate and put out somatostatin. Yeah.
And would you have high acid if your stomach was empty and you're done digesting? Is that like when they would send that out?
Yeah, that's a possibility. Or if you have food in your stomach and you you're gonna be putting out acid because of that. Because when you have those amino acids, it's gonna trigger gastrin, and gastrin will trigger acid release.
It's like a negative feedback thing.
Yeah. So there's this activation where food is present, but it inhibits itself to prevent it from basically putting out too much hydrochloric acid and too much enzymes. Can I move on? Yeah? All right. We got 2 nodes. I guess good enough. So there's also a mucus bicarbonate layer. So here we have our mucosa here, and there are these cells called gastric mucus cells. That's what they're called, gastric mucus cells. And their whole job is to put out mucus and put out bicarbonate. So we have bicarbonate, and there's this layer of mucus. And so what is mucus? So mucus is made up of a protein called mucin. And so this is what mucin looks like. And so mucin does something which a handful of other compounds do. They link together with each other, and so this is basically a mesh of mucin. You can kind of think about it. It's just this kind of random mesh of all these mucins line kind of hooked together. And what happens here is within this network of mucin, they can hold water. Right, and so from this network they can hold water within this network. And so you have water being held by this mesh-like structure. We're talking about the molecular level, so this is a molecular level mesh. What does this make? This makes a gelatin. This is gel. A gel is basically a molecular mesh that holds water. So Jello is like this. Now Jello is not made of mucin. Mucus is made of mucin. Jello is made out of some other molecule that acts like mucin. All molecules that make gels act like mucus, where they make this kind of mesh at the molecular level and then trap water or trap some other liquid inside the mesh. And so that's why, even though it's solid, it has this kind of liquid feel to it. That's what gel is, and that's what mucus is, right? Mucus is just basically gelatin. It holds water, but it uses mucus to hold it all together, or mucin to hold it all together. So we have this kind of thick mucus layer, and then within this mucus layer, we're suspending bicarbonate. So what is bicarbonate good for? Buffer, acts like as a buffer. So if we have this mucus layer, we have this bicarbonate ion here, we've basically made not only a physical barrier, but we've made a pH barrier too. And because of the bicarbonate, even though we have acid in our lumen, the cells at the mucosa are not affected by this acid because of this bicarbonate mucus layer. And you see in this picture, in this layer, it's roughly 7, a pH of 7. So it's roughly neutral, even though somewhere in the lumen, we have a pH of 2. Mucus is also really good because it acts as like a physical protectant, right? So you're not going to have food scrape against your epithelial tissue and break that up because there's this nice protective mucus layer there too. It also kind of helps lubricate food a bit too. So it kind of acts like saliva in that sense too. And so those are a handful of reasons why we produce mucus. So we can host bicarbonate ions for pH buffering. We have a physical barrier to help protect against mechanical abrasions. And it helps kind of lubricate the food a little bit more too. Question?
So that bicarbonate is in the mucin gel?
Yeah, so the bicarbonate is also just like water, it's suspended within the gel. Just kind of how you can put flavor in your jello by suspending it in the matrix of jello.
Is that what makes ibuprofen, does that stop the mucin being generated?
So ibuprofen, or I mean Pepto-Bismol?
No, ibuprofen.
Oh, ibuprofen.
If you take too much, you end up ruining the acid or doing something with the acid.
Yeah, ibuprofen just basically elicits more of a pridosol response is all. Yeah, and so that's why we have a mucus layer in our stomach. We actually have a thin mucus layer all throughout as forms of protection, but we have a really thick one for the stomach to help with the acid buffering and the physical barrier too. All right. So here we have our stomach here, the end of our stomach, and it dumps into the first part of the small intestines. So this then kind of marks the beginning of a new phase. We're no longer the gastric phase because the food is now leaving our stomach, so now we're in the intestinal phase. It's pretty much the third and final phase of the digestion process as a whole. And so moving into the small intestine, moving into the first part of the small intestine, the duodenum, we have a whole bunch of what we call accessory digestive organs. Organs that are not directly part of the GI tract, but input into the GI tract. So the first one is the liver. And there's the gallbladder. So the liver and the gallbladder will have this common bile duct that will then kind of empty out into the small intestines, into the duodenum, and it puts out bile. Bile is used for, is basically used to help absorb fat, which we'll talk about maybe today, maybe next time. And then you can kind of see this organ right here, this one here. This is the pancreas. And the pancreas also has its own opening, this tube here that kind of also dumps out into the small intestine. So the pancreas will put out enzymes, and it puts out more bicarbonate. Yes?
You call that part the duodenum?
The first part, so the small intestines, you'll learn this in anatomy if you haven't taken anatomy yet. The small intestines is broken up into three parts: the duodenum, the jejunum. Can I spell this right? I think that's, that might be an E, but whatever. Spelling doesn't count in physiology. And then the ileum. Well, they're not equal in length. The ileum is much longer than the other two parts, and they have different anatomy at the molecular level. If you just look in intestines, you're not going to really know the difference between these three. But yeah, no problem. So the pancreas will put in enzymes and bicarbonates. And so this part where the stomach meets the small intestines and the enzymes and the bile enter, this is actually a really important part for control, because this is the part that helps dictate how much of the chyme gets to enter the small intestines, because small intestines, its main job is absorption. This is where the majority of absorption occurs. Now, of course, there is some secretion, there's motility, there's still some digestion occurring. All of those are still happening, but this is where the majority of absorption is occurring. Yeah. We're not including, of course, alcohol is being absorbed here, but that was also being absorbed in the stomach. And so we have, there has to be a regulation of how much chyme can come into the small intestines, because we want to maximize how much absorption is occurring, right? So let's say this is our absorption chart. And this is our max level absorption, right? Right. If we put in this much food, we could absorb all of it, right?